Okay, good morning, everyone. We'll begin session J07, Wide Field Radio Astronomy and Survey Science. Myself, Mike, and Isabella Prandoni were the co-conveners for this. Isabella is unfortunately unavailable to be here this week, but the rest of us are great to see this very exciting session, which will begin with Andrew Hopkins talking about the EMU survey.
Thank you very much, George. And thank you for coming. Thank you very much to the organisers for giving me the opportunity to talk to you about EMU today. How do I fast forward the slides? The green button? The big one. Right, there's two green buttons. Excellent. All right. Yeah, so thank you very much to the organisers for giving me the opportunity. Well, is that like really deafening up the back? No? All right, very good. It's just deafening for me. I can manage. EMU. EMU is the evolutionary map of the universe. Looking around at the audience, I'm pretty sure that at least half of you have already seen 90% of this presentation. And I apologize to those of you for the repetition. For everyone else, EMU is going to be and is becoming very rapidly the touchstone atlas of the radio sky in the Southern Hemisphere. We are mapping the entire Southern Hemisphere with the ASC Radio Telescope, and in so doing, will support science that spans a vast range of topics, some of which are mentioned in the slide here. EMU has been going for a long time. It started more than 15 years ago now, and was the concept of Ray Norris, who was the original project leader. I stepped into the project leader role from Ray when he decided to step back and focus on science rather than politics just a couple of years ago. And over that period, we've seen ASCAP go from concept to real physical instrument through its commissioning and early science phases, now into its production mode. And EMU has gone from strength to strength as part of it. So EMU is mapping the entire hemisphere. It's a survey at around a gigahertz, about 943 megahertz, 288 megahertz bandwidth, the usual ASCAP low band stats, with a resolution of about 15 arc seconds and a sensitivity getting down to about 25 microjanskis over the entire hemisphere. And I like to pause on that for a second, because going back almost 30 years now, my PhD project was a wide area deep radio survey with the Australia Telescope Compact Array, which had very similar stats in terms of sensitivity and resolution, and it covered about 3 square degrees of the sky. EMU is doing that like 10,000 times over. So the adage that you are fated to redo your PhD throughout your career until you've got it right has come home to roost. So EMU is awesome. And although the survey is not complete, it's been supporting a vast range of science. I will show you a few highlights if I haven't already exhausted my time towards the end of the presentation. But please go and have a look at the papers list. We have an ADS library you can get to from that QR code, or you can Google it. And there are more than 80 refereed EMU papers out there already, and we're barely scratching the surface. This slide is a little out of date. The observations are actually now, I think, when I looked a couple of days ago, 41% complete. This is a map showing the tiling of the hemisphere that we are doing with EMU, and the filled squares, which you can't really see much of apart from kind of little grey blobs. That is actually real EMU data, however. Those little grey blobs are the tiles that have been completed and released so far. And as I said, we're about 40 complete now. We're anticipating the rest of the EMU observations being finished in something of the 18 to 24-month timescale from now. All right. I've been talking about EMU for quite a while, and some of the slides actually go back to earlier incarnations of this presentation, and I've left them in on purpose because the story of how we got here is, I think, almost as interesting as where we are right now. As ASCAP was going through its commissioning phases, we did a number of pilot surveys. It observed pilot observations for all of the various ASCAP surveys, and EMU was no exception. EMU Pilot 1 was a large contiguous extragalactic area, about 270 square degrees, so already something like 100 times bigger than my PhD project. And it produced huge numbers of awesome results straight off the bat, even before we got to the main survey. And so I've just thrown a few pictures up to give an illustration of that. This all comes from Ray Norris's Pilot 1 paper from 2021. Please go and have a look at that if you want all of the gory details. But one of the exciting new results that came from the EMU observations was the discovery of this class of radio object referred to as AURCS. AURCS stands for Odd Radio Circle. We currently believe that these are examples of emission associated with some extreme event in the galaxy, which has produced this shell of radio emission that's extending well beyond the galaxy itself. We don't think that it's associated with radio jets, standard AGN black hole type emission, which you see in, for example, the dancing ghosts in the top left. But the mechanism that produces the AURCS is still not well constrained at all. It's a new class of object, and it's one of the unknowns that we were predicting, that Ray had predicted, that EMU would discover simply by virtue of observing such a large parameter space in terms of sensitivity and area. And we fully expect that there will be more new, unknown types of sources that EMU will continue to discover. And just because the data is amazing, I've put together just some pretty pictures to share with you. This is just a montage of double lobe radio sources. If you start looking through the EMU data, and you can, it's all available online. If you go to emusurvey.org, you can find the Aladdin Light browser, and our technical lead, Josh Marvel at NRAO, has put together HIPS versions of all of the EMU images, and you can just explore them. Go and have a look. All right, I will, in like 2 minutes, do a whiz through some science highlights. I'm not going to talk about any of the science in any detail. I'm not going to do any of it justice. Some of the early results have focused on galaxy clusters, largely because you can do amazing science with a single observation rather than needing large areas of the sky. So, and I should have references to all of the papers that have presented these results. So if you want to actually dig into the gory details, please have a look at the slides on the recording, find the references, and go to the source of truth. This is the Corkscrew Galaxy. This is one that Bebel Korobalski spent a lot of time exploring. Very unusual radio jet with characteristics associated with some kind of helical structure, possibly due to rotating black holes or something very complex going on. More galaxy clusters. Stefan Duchesne, at my prompting, put together a census of clusters. So not looking at clusters individually, but trying to look at the properties of clusters as a population. And I think that this is really the first step towards something much larger that we would like to see as more of the EMU data comes through. And nearby spiral galaxies are also showing up very strongly with EMU through the star formation processes that are associated with the radio emission that they produce. So this is just a montage showing you the radio in front of the grayish, partially transparent overlaid on the optical. You can see that spiral galaxy there. I have a master's student starting with me literally this week. He landed from the US just yesterday and is probably still massively jet lagged and maybe even still asleep. And he's been tasked with the challenge of looking at all of our nearby resolved spiral galaxies in EMU to understand the links between the radio emission and the star formation that we see in the optical and the infrared, to understand why they are different in different places. There are very obvious asymmetries that we see in some of these objects in terms of differences between the radio and the infrared emission. We're just starting to explore the properties of galaxies in EMU. This is some work that was done by my current PhD student, Jahang Prathat, who identified a population of low mass, low radioluminosity AGNs that are otherwise undetected in traditional AGN diagnostics, such as the BPT diagram or the infrared color diagrams. We knew that these galaxies should exist, but without the radio measurements, they're actually quite hard to identify. This is some work done by one of my other PhD students, Tanya Ahmed, who's just recently completed her PhD. She's on the job market and she is awesome. So if you are looking for postdocs, please talk to Tanya. This was the first paper that she did as part of her PhD project, where we looked at the radio counterparts to optical galaxies from the Gamma survey. Ask me about Gamma later if you would like to know more details. And what we discovered is that as you go down to the very low mass end, 10 to the 9, 10 to the 8.5 solar masses of galaxies, you still find radio counterparts to these galaxies, but the ones that you see tend to favor dusty galaxies. And we don't know why. We don't know why there are galaxies at that low mass end that have relatively little dust that we should be able to detect at radio wavelengths, but we don't. So that's another interesting puzzle. I think it has something to do with the mass distributions of the way that stars form, and that might be different in different galaxies. I have a different PhD student working on that. However, we can also use the fact that measuring the radio emission in star-forming galaxies is a direct tracer of their star formation rates. And if you look at other traces of star formation, in particular the H-alpha, which is very heavily affected by that dust obscuration, it turns out that at the high star formation rate end, you miss a lot of the star formation that you might otherwise be seeing because of the obscuration at H-alpha wavelengths. In the radio, you can pick that up and you can do a calibration to correct for the optically thick dust that otherwise never escapes, that you will never be able to correct if you're only measuring the light from star formation at optical wavelengths. So this is a result from two papers. Brianna Farley's paper has been published. She's a master's student at Queensland University of Technology, and she's also on the job market. She's also awesome. And Tanya's companion paper to that is still undergoing review. I've spoken a lot about extragalactic science because that's my particular area of interest, but EMU obviously is also covering the Milky Way. This is a picture of the Milky Way, and 5 points to anyone who can spot the constellation in that picture. But when you look at the Milky Way at radio wavelengths, it looks vastly different. And this is just that montage again, showing you the overlay of the radio and the optical, because I think it's incredible that we have so much data and there have been a huge number of papers already on EMU data, even going back to the early science and pilot data in the Milky Way with EMU, looking at properties of supernova remnants, looking at properties of pulsar wind nebulae, looking at newly discovered large supernova remnants. This is one of the papers that Miroslav Filipovic published not too long ago on a relic supernova remnant called Diprotodon. Diprotodon was one of the Australian megafauna, now extinct, probably thankfully. It was a giant wombat, very, very large. There's a picture of it, but the thing in the top left there is not a bear, it's actually an extinct Australian megafauna, giant wombat called Diprotodon. The supernova remnant was given that name because of its massive, massive size. The green circle shown in that picture was the previously known extent of that supernova remnant. With the EMU data, its size has more than doubled. More amazing supernova remnants, this one called Telios. And if I'm remembering my Greek, Telios means perfect. This is the perfect circle. And that's saying something about the environment that supernova remnant's been expanding into. More supernova remnants. This one is unusual in terms of its X-ray properties. Again, way beyond my level of expertise. But it's not just about the science. We've also been developing novel techniques for exploring the data of necessity. Trying to identify complex radio structures in an automated way is not a simple problem. There have been many approaches that have been developed to try to do this. So there is a complexity metric approach. So that's Gary Segal, David Parkinson developed that. There's machine learning approaches for automatically identifying extended radio structures. So Nikhil Gupta's been leading that effort. Simona Righi has also been using neural networks for identifying complex radio structures. And there's actually a lot more than that as well. I have a PhD student, Lachlan Barnes, who is currently in the process of comparing the performance of all of these different techniques. When you do that, it turns out that they're all fantastic at finding these things, but they all find slightly different populations. And please ask me about that later. That's, I think, a very exciting result. Radio Galaxy Zoo, we're connected very closely to our citizen scientists, and the EMU data has been informing the latest generation of Galaxy Zoo using radio images. So Hongmin Tang and Eleni Varoulakis have been leading that effort. Have a look at that. This is another piece of work that Nikhil Gupta has put together. It's called EMUs, the EMU source exploration. No, EMU search engine, that's what it is. Search engine, source exploration, I think works as well. You can just type in bent tail radio galaxy and it will find all of the bent tail radio galaxies for you. It's a kind of a combination of large language model approaches to deep learning with radio images. So you can go there, you can explore. It's still in the early stages of development, and Nikhil and myself would be very happy to hear feedback for suggestions for improvements. But there's already a lot of functionality available. And obviously, all of these exciting discoveries have a lot of interest more broadly than just astronomers, and we've been trying to promote them quite heavily in the media. You can see that we favour the conversation as an outlet, but this is not the only place that the new results have been hitting the press. EMU is not a one-person show, as hopefully you've already been able to identify. We have a team of over 400 people around the world. The data is all public, it's all on Castor. The value-added data products are proprietary to the team, and they will be progressively released through official data releases as we get further through the survey. But But please get in touch with us if you want. If you're not already involved and you would like to be, let me know. I will stop there. Thank you very much, George. Thank you, everyone.
Thanks, Andrew. We basically burned through the question time, but I'd like to give Andrew an opportunity to answer one quick question if there is one. Yep, Tara, do you mind standing up to that microphone right behind you?
You didn't tell us much about the cosmology that you'll do with EMU. Do you want to give us like a quick summary?
Sure. Thank you for the prompt, Tara. Yes, EMU cosmology really is waiting on more of the survey area to be completed. However, the cosmology team, and it's being led by David Parkinson and Benedict Barkalis, has identified a number of projects that they can do with the circumpolar coverage that we currently have. And I can't remember off the top of my head exactly the survey area, but it's got to be something like a couple of thousand square degrees at this stage. So there are at least half a dozen cosmology projects that are literally kicking off right now. There have been a few precursor bits of cosmology science, cross-correlation work looking at the results in the pilot survey between EMU and the higher frequency satellite data from Planck, for example. But it's really still quite early stages for the cosmology work. But it's looking quite exciting.
Excellent. All right. Thank you very much, Andrew. Let's thank Andrew again.
Thank you.
A talk which very much basically defines the title of the session. Thank you very much. So our next presentation will be by Elizabeth Mani, who will talk about the ASCAP flash survey. 3 minutes before questions.
Okay, thank you. Thanks, George. Thanks, everyone. Where's the big green button? Okay. Hi, everyone. My name is Elizabeth Mani from CSIRO, and today I'm going to be telling you a little bit more about another large survey currently being carried out with ASCAP, which is the ASCAP Flash survey. There we go. So FLASH is the first large absorption line survey in H1, and it's essentially a wide area survey being carried out with ASCAP to search for the 21 centimeter H1 line in absorption. And the frequency range of ASCAP lets us detect that H1 at redshifts between 0.42 and 1. So the ultimate aim of FLASH is really to probe the cool neutral gas at these intermediate redshifts. And we're doing that using in an untargeted approach to a wide area survey. So like all of the large ASCAP surveys, we're quite a large team spread across the globe. And the PIs are myself and Elaine Sadler, who's also attending this meeting, if you have any FLASH-related questions. And our project scientist is Hein Yuen, who was recently based at the University of Sydney, but has since moved back to the Seoul National University to take up a fellowship there, but is still very actively involved in FLASH. So broadly speaking, to place this into some context, there's two main techniques that we have used to probe the cool neutral gas content of galaxies. And so at low redshifts, I probably don't need to tell people in this room, but we can detect neutral hydrogen, trace the neutral hydrogen property of galaxies by detecting the 21 centimeter H1 line in emission. And that produces these lovely images you see here that shows us that the H1 disk in galaxies can extend much, much further beyond what we can see in the optical. However, the H1 line in emission is inherently weak, so this becomes increasingly difficult and requires a lot of telescope time to go out to higher redshifts. Really, anything above redshift 0.2 requires a lot of telescope time until future facilities like the SKA come online. At the other end, we also actually have quite a lot of information about H1 in galaxies at higher redshifts, thanks to studies of DLAs, or looking for the Lyman alpha absorption against high redshift quasars. And at redshifts above about 1.7, the Lyman alpha line is shifted into the optical bands, which means that we can search for these absorption lines using optical telescopes on the ground. But at redshifts below this threshold, then it's in the UV and you really need to go to space, which makes it challenging to build up very large samples of these sources. So what we're aiming to do with FLASH is to start filling in this gap in the middle. So you can see here this compilation put together by Zhongwan Ri. And so we have quite a lot of information at high redshift. This is coming from DLA studies at high redshift. And at low redshift, we have quite a lot of results based on H1 emission line studies. But with FLASH, we're going to try and get better constraints at this redshift range of 0.4 to 1. And that's a really critical time in our cosmic history, because we know that the peak of the star formation rate in galaxies peaks around redshift 0.1, redshift 1 to 2. So by probing this time between redshifts 0.4 and 1 is when the star formation rate of galaxies is in rapid decline. So understanding what the neutral gas is doing in these galaxies can help piece together that puzzle. And we can do that by searching for absorption lines. And that has the advantage that unlike H1 in emission studies, which is highly dependent on the redshift, where our sensitivity is mainly driven by how bright the background radio source is. So it's not a redshift dependent sensitivity limit. And that means we can detect it out to much higher redshifts, provided there's a bright radio source in the background. We're also more sensitive to the slightly colder gas, which is around about 100 Kelvin. But as I said, we can only trace a H1 if it happens to lie along our sight line between us and a bright radio source in the background. So to carry out this survey, we of course are using ASCAP, the Australian SKA Pathfinder, located in Yalimana Ilgaribundara, CSIRO Rose Murchison Radio Astronomy Observatory on the lands of the Wodjri Yamaji. So I'm not going to go too much into details about ASCAP, but I think I just wanted to really highlight 3 key features, which is really important for FLASH. So first of all, ASCAP, the phased array feed, gives us a large instantaneous field of view. And so that means that we can survey the whole sky quite quickly. It's also on a very nice radio quiet site, which opens up this frequency range of about 700 megahertz to 1 gigahertz, which in other sites is often blasted by RFI. And we also have quite a wide bandwidth. So with ASCAP, we get a 288 megahertz instantaneous bandwidth. And when we're looking for H1 in absorption, that actually gives us access to the redshift range of 0.4 to 1 in a single pointing, in a single observation. So taking these 3 kind of key capabilities of ASCAP really informed how we designed the FLASH survey. So it's designed to be a large area, but relatively shallow survey. So we cover all sky south of declination plus 15, but excluding the galactic plane, because it's just a bit messy. And that corresponds to 600 fields corresponding to 24,000 square degrees. But we're only doing 2 hours per pointing per field. So it's a much shallower survey than other surveys such as ASCAP or Wallaby. And we look for the 21 centimeter absorption line towards every radio source that's brighter than 30 millijanskis in continuum flux. So we extract a spectra towards every single source in the field above that flux threshold. And we're not doing any extra selection based on optical properties or redshift or anything like that, which is very different to how previous absorption line studies have been done. So for our H1 detections, they can broadly be split into 2 categories. The first is what we call intervening absorbers. And that's where the H1 absorption line we detect is somewhere along the line of sight between us and the background radio source, or associated absorbers. And that's where the H1 we detect is associated with the same galaxy as is hosting the background radio continuum source. And using these 2 broad categories, we can address 2 kind of key science aims for FLASH. The first with the intervening absorbers, that gives us a sample of purely H1 selected galaxies in this intermediate redshift range. And that allows us to put constraints on the cosmic evolution of H1 and put constraints on the cosmic mass density at this epoch between redshifts 0.4 and 1, as well as putting some constraints on the average spin temperature in galaxies at these redshifts. And then we also have the associated absorbers, and that's really telling us about AGN fueling and feedback mechanisms. So starting to probe how these radio jets, these powerful radio jets, are interacting with the cool neutral gas in the interstellar medium of these galaxies. So where are we at so far? We have completed, similar to the EMU survey that Andrew just talked about, we have completed 2 pilot surveys, which totaled more than 200 hours of observing time and covered about 3,000 square degrees of sky. So that was published earlier this year by HeyNew. You can find on that archive link there. And I've also got a QR code in one of the following slides. And as of May 2023, we've commenced our full survey operations. So we're at the moment just shy of about 30% complete for the survey. And we've recently restarted our observations again in the last couple of weeks. So we're expecting that number to keep ticking up slowly over the next couple of months. All of our data is automatically processed by the observatory. So it's processed through the ASCAP soft pipeline and automatically uploaded to CASDA, already processed and reduced. And so the first time we really interact with the data is to get those science-ready data products from the ASCAP archive, CASDA. And then we've also built up a collaboration with the AusSRC, the Australian SKA Regional Centre, who have helped us build a bespoke Flash database, which then we also use to do a small amount of processing and things like running the line finder to help identify these very rare H1 absorption lines. And this is just a graphical representation of where we're at so far. So the orange squares will represent the full Flash survey once we're complete, and the black areas are the ones that we've already completed and had observed. So you can see we've prioritized areas of the sky either along the equator or corresponding to the DESI region to maximize the multi-wavelength data that we have available for these early science results. Okay, so now moving on to some first early results. First, I wanted to highlight was our results from the Flash pilot survey. So this was published by HayNew, and you can see we've discovered at least 30 new detections. These are detections that we're really confident in of H1 in absorption at this redshift range between 0.4 and 1. And you can see already from this gallery that our detections that we're finding cover a broad range of properties. We've got very strong broad lines, weaker, very narrow lines, and things like that. So what we also found when we were looking at our detection rate for the pilot survey is that we're finding these sources at very high optical depths. So you can see on this plot here, these points kind of in the top left corner of that plot have peak optical depths above 1. So these are very high column density absorption lines that you generally wouldn't detect by doing a more targeted approach and selecting a sample based on redshift and following those up. So it's only because we're doing this approach of having a large area that we're able to find these much rarer, more extreme galaxies. And we're expecting a lot more of these to come out with the full survey. We're also finding that most of our sources have optical counterparts. That was using the DESI legacy survey, and they're often quite massive galaxies detected in WISE and infrared data, and often associated with groups or close companions, which is not necessarily what we were expecting. We might have been picking up very, very dusty sources through their H1 line. And so far from our pilot survey detections, we seem to be dominated by associated systems. We're not seeing as many intervening line systems as we first estimated. The second thing that we found I wanted to highlight from our pilot survey results is a very large fraction, over 65% of our detections are associated with galaxies that have this characteristic peaked radio source spectrum. So this is work being led by Emily Kerrison, who's speaking after me, so I'm not going to go into too many details and steal her thunder, other than to plug her paper and also this code that she wrote, Radio SED, which is all published and publicly available, and can go through taking any radio data and find the best fit model to the Radio SED, as you can see here on this plot. But what this is telling us for Flash is that these peaked radio spectrum sources are often associated with very young compact radio AGN. So for Flash, we may be detecting these radio galaxies at a very specific point in their evolution. And that is also backed up by the other follow-up we've done with using VLBI. So we have followed up all of our Flash H1 absorption line detections from the pilot survey with either the LBA, the long baseline array in Australia, or the very long baseline array in the US. And although all of our detections are unresolved with ASCAP, so they're compact with ASCAP, when we go to VLBI scales, we're starting to then resolve them into separate components, into separate radio jets. And these generally are on the scales of a few hundred parsecs to a few kiloparsecs. The other really important thing about having the VLBI follow-up and having high resolution radio continuum data is that it allows us to place stronger constraints on the covering factor, which is a key assumption that we that we need to use when estimating the column densities we're getting for our flash detections. And the last early results I wanted to share with you all today is one of my favorites. So this is Parkes 0409-75. It's one of the most powerful radio galaxies in the Southern Hemisphere and was one of our first detections we actually got with ASCAP, I think in early science, or maybe even with beta using only six antennas. And we detected this one in H1 in absorption, but we noticed that the H1 absorption line was offset from the optical redshift of the galaxy by about 3,000 kilometers per second. So doing some deeper optical follow-up, which is what you can see on the right here, we noticed with deep Gemini optical imaging and then spectroscopy that there was another galaxy associated or superimposed in front of the eastern southern radio lobe. And getting a spectrum of this second galaxy, what we call galaxy B, confirmed that that's actually at the same redshift as the H1 line. So the H1 we're detecting is from this galaxy in front of the radio lobe, not associated with the AGN host galaxy. But because this is such a well-studied radio galaxy, we dug into the literature and found previous publications looking at the polarization of this source and mapping the rotation measure across this very powerful radio galaxy. And that paper noted that the eastern lobe had excess depolarization and a high rotation measure, which once you take that information and piece it together with the fact that now we know that there's an intervening galaxy with a lot of H1 in the way, that allows us to estimate the magnetic field of a galaxy at a redshift of about 0.7. And that gave us a rough order of magnitude of about 15 microgauss, which puts it in the same regime as a typical star-forming galaxy. So I just thought this was a really neat example of how H1 absorption lines, combined with other data, were able to tell us something about the magnetic field of a random galaxy at redshift 0.7, which I think at the time was one of the highest redshift magnetic field galaxies that we had. So on my final slide, a theme that you might have noticed when going through, when I was talking through all these first results from the ASCAP flash data, is virtually all of those first results heavily relied on having multi-wavelength data. And generally speaking, we can separate this multi-wavelength follow-up and the data we need into two broad categories. So we need information over basically the whole survey field. Things like optical photometry, redshifts are really useful, not only for our detections, but also for our non-detections to provide constraints on how many intervening lines, how many associated lines we're seeing and things like that. And then, of course, we also want to do more targeted follow-up of specific objects of interest. And things like follow-up with MUSE, ALMA, VLBI have already proven to be very fruitful. So I will leave my summary there, other than to finish up saying that the ASCAP Flash survey is well underway. We're almost a third of the way through the full survey, and we've already published our pilot sub-survey results. So I encourage everyone to go and check out Haynes' paper on the archive. And yes, multi-wavelength data, I think, will be crucial to maximizing the science from this survey. Thank you.
Thank you, Elizabeth. Great talk. Any questions? Randall, thanks.
Really interesting, thanks, Luke. I think it was on your key result 2, or first result 2, where there's the turnover. It went past so quickly. Was there a characteristic frequency associated with the redshift of the absorbers for these sources?
That is a very good question. And I would point you to Emily, who just subtly shook her head. So no, I think there's a range of peak frequencies that we're seeing from the sample.
Thanks.
Sorry.
That's all right.
Any other questions? Yes, Ruta.
Are there visibilities available for these data, or how are you managing? What are you retaining from the visibilities, if at all?
That is a very good question. So all of the ASCAP surveys, what we interact with mostly in the archive are the science data products. So the average visibilities are also available in the archive. The spectral line visibilities, because it requires each field has such high data rates. I'm not sure if the spectral line visibilities are stored. I don't think so. No, Matt is shaking his head. No, so we do, if we find any issues with the data, it's generally more efficient to just reobserve that field rather than trying to go back and reprocess and update our processing parameters. So if there's any issues with the data, we generally just chuck it out and start from the beginning.
Perhaps one last question before we move on. Anybody? No? Okay, if not, let's thank Elizabeth again.
Thank you.
Okay, so our next talk is by Emily Carrison, who's going to tell us about compact radio sources. I won't read the rest of your slide.
Bit of a long title, but fine. Okay, yes, so thank you, George. So I am a PhD student working with Liz and Elaine and Vanessa in the Flash team. And I'm going to be changing tack a little bit. Already we've heard about 2 really excellent wide field ASCAP surveys. So I'm going to be talking about a specific use case where we can combine lots of these wide field surveys to do some interesting science. So I have a very long title, but essentially what it amounts to is I'm going to talk to you about compact sources and how we can benefit from lots of wide field surveys and combining the data to do some interesting science. So as we're in Australia, we often like to start with an acknowledgement of country. So we are, of course, on Tumbalong, which is the land of the Gadigal people of the Eora Nation. But I'm actually going to borrow an additional acknowledgement that Ron Akers first did in the conference a couple of weeks ago, the Dynamic Radio Sky. And I would also like to acknowledge a lot of the traditional knowledge that is in Australia. We know that a lot of Australian Indigenous people thought a lot about the sky and the stars. And they actually already had a lot of knowledge of twinkling of stars. This twinkling or scintillation effect is something that I will talk about a little bit later in my talk in the radio. But as you can see here from this quote from a Waterman elder from the Northern Territory, there was already a lot of cultural knowledge about twinkling and how it could be used for science. So with that in mind, I'm going to talk you through a little bit of wide area surveys and combining them. So I want to talk first about experimental use for wide area continuum surveys in particular, identifying some of these sources with this characteristic peak that Liz talked about previously you were seeing in the Flash survey. I'm going to talk about some of the previous samples that we had before these wide field surveys really became a big driver of new science, and what we can do now that we have many of these wide field surveys and lots of this new data coming out. Then I'm going to talk about how we can add extra dimensions to this science by using additional surveys, including the ADCAP Flash survey to get some spectral line information, as well as getting some temporal information from the ADCAP-RASC survey and from a new survey looking for IPS signatures with ADCAP as well. And finally, I want to talk about how we can then build on these wide field surveys using selective follow-up with specific telescopes to really extract the most information we can from our data. So to start with, as Liz already hinted at, I'm interested in these peak spectrum sources. So these are generally powerful radio AGN that have a characteristic peak in their broadband radio spectrum if you look at it over a wide range of frequencies in radio. Historically, these were split up into different categories, so there were the CSS and the GPS sources, but now we know that these are basically part of one continuous distribution of sources peaking at a range of frequencies, so we just tend to call them peak spectrum or PS sources. And in terms of the physics, we know that these sources are very, very compact. As Liz showed in the VLBI follow-up of the Flash sources, they tend to have linear sizes of less than about a kiloparsec. So they're very, very compact, and we know that this spectral turnover is typically due to some kind of absorption at the location of the radio emission. So that can either be free absorption if it's some cloud in and around the radio emission, or it can be synchrotron self-absorption in the jets themselves. Either way, they're in a very, very dense medium, which makes them interesting to study for a wide range of physics. In particular, for us in the Flash team, it's a very good way to probe the dense ISM in and around these AGN. And we know that these sources are, for the most part, recently triggered. So within about 100 to 1,000 years of triggering of the radio jets, which is also very interesting because it allows us to really, again, study this particular evolutionary phase when there's really interesting things happening in terms of jet triggering and maybe also AGN tube cycles. In terms of detecting these sources, as I've already hinted at, you can see the peak at a very, very broad range of frequencies, and that's also confounded with the effects of redshift. So a peak at a very, very high frequency, but very, very far away, will look much lower in the observer's frame. We know if we look at large samples of these things that the peak of the frequency, the peak at which the peak of the frequency, the peak of the flux density is what I want to say, is approximately proportional to the linear size of the source. And we also, the inverse of the linear size of the source, I should say, and the size is approximately proportional to their age. So we have this from sample statistics, and we can also look at the age of these sources if we can do highly resolved VLBI to track the hotspots and extrapolate from the speed of the hotspots to how old the jets might be. We also have a nice agreement between simulations and observations that basically show this nice relation where as the source gets larger, the peak frequency shifts down. All that to say that if we want to study a broad range of these things at a broad range of redshifts, we actually need broad frequency coverage in order to detect all of them that are out there. So in terms of what's been done so far, before we had lots of these lovely wide area surveys that we have with instruments like ASCAP and the MWA, the samples are pretty limited. You know, we had samples of maybe 100 sources. That was considered a very, very big sample of these things. Often each individual source had less than about 5 flux density measurements. You can see some early examples of these peaked SEDs from a paper from the 1970s here. A lot of the curves were drawn by hand, which I think is quite nice, but it did mean that they were not really covering the full range of parameter space that in which these peak spectrum sources exist. Things got a bit better in the 80s leading into the early 2000s, where we had additional targeted observations with instruments like the compact array. So we could get much more detailed structure for individual sources. And we had some larger samples, but again, we really were limited to samples of sort of less than 200 sources or so. So the question, of course, is, can we do even better? And hopefully the answer is yes, now that we have wide field surveys. So first of all, we had the GLEAM survey with the MWA, and this was really a turning point in the search for these peak spectrum sources. So Joe Callingham and his collaborators came up with this really, really nice large sample of these peak spectrum sources, about 1,500 of them. So you can really start to do nice sample statistics with that many sources. But they were really focusing on the GLEAM band. So most of their sources were very, very bright because GLEAM had a sensitivity limit of about 200 millijanspeeds, yes. And most of these things were peaking at about 300 megahertz or below. So these things were relatively large on the scale of compact peak spectrum sources, or they were quite far away. That's it. There was a lot that could be done with them. A couple of years later, Kat Ross looked at the variability of these things, and she was able to identify variability just based on the multiple epochs of GLEAM data or of MWA data that existed at the time. That's exciting. There was already a lot that could be done with the GLEAM data, but again, we've got more data now, and with surveys like INU and FLASH and the RACS survey, we can now extend this to higher frequencies as well. So that's first of all where my fitting comes in. So we have this radio SED fitting that compiles data not only at GLEAM frequencies, but at higher frequencies as well. And that's really because a lot of these peak spectrum sources actually have slightly complex, subtle SEDs if you look at them in a bit more detail. So this plot on the right of my slide is one such example of those. So you can see that it actually has a low frequency turn up in the GLEAM band. And so that's probably an indication here of multiple epochs of radio AGN activity. So being able to identify things like that is also interesting in the larger context of sort of AGN duty cycles. So we have this radio SED code that actually compiles flux densities from pretty much all wide area surveys that are focused on the southern sky. So that extends from NBSS in the 90s all the way through to the recent RACS surveys in the last couple of years, and all the way up to ALMA as well. So we're really covering both a nice space span of time and frequency space. And we can do Bayesian model inference and comparison to get really, really nice statistical measures of what the best fit SED is and really make sure that we're identifying true peak spectrum sources when we see them. And if you look at just the number of statistics, when the Callingham sample came out, we had about 1,500 peak spectrum sources. Just looking at the number of sources we have alone across the southern sky, we have several orders of magnitude more sources to be fitting. So that's a really nice indication that we're going to have much larger samples again of these peak spectrum sources. The other nice thing we can do with radio SED is we can actually start incorporating upper limits from surveys where there are nicely published detection limits in terms of flux densities. So these are 3 peak spectrum sources here that we have identified using the fact that surveys like the AT20G survey at 20 gigahertz had really nicely published flux density limits and completeness limits. So if we have things like that, then we can actually identify sources where non-detections are really, really crucial to identifying these compact peak spectrum features. That's a nice thing we can do now as well with wide area surveys. And to put all this together, I've looked at a test case. So I've looked at the Stripe 82 field to see how many peak spectrum sources we could identify there, and then what kind of science we could do with this new sample that we come up with. So this is a very nice 300 square degree field on the equator. So there's lots of multi-wavelength data and obviously also lots of radio data, which is why I'm looking at it. So we have about 3,000 fittable radio sources in this field where we can do the radio SED fitting. I'm not sure how well this shows up on the screen. Unfortunately, not as well as I was hoping, but that's supposed to show you the distribution of continuum radio survey sources from the RAP survey. On top of that, these were the known peak spectrum sources before I got to the field. There were not a lot of them because, again, we needed often targeted follow-up to identify the peaks. So if we combine all the wide area surveys we have to date, do the SED fitting, now our sample looks something like this. So this is really exciting. Even from this 300 square degree field, we're getting over 300 peak spectrum sources. So this is a really nice indication that it's going to be really easy to do these population scale, large sample statistics studies where we can say something interesting about how these sources evolve and what kind of environments they're in. These are what some of the sources look like. So as you can see now, we're detecting these sources that peak as low as 100 megahertz in the Gleam band, right up to things peaking at several gigahertz, which are very, very compact, probably very, very recently triggered, thanks to data like data from the ALMA catalog and also the AT20G survey. So that's how we identify them. Now we need to think about what science we can do. And again, this is really where the wide field surveys and combining them really starts some interesting science. So the first thing that we did was to look at the long-term variability of these sources. Typically, you would not expect much variability in a peak spectrum source because the jets are not aligned along the line of sight, so you're not getting beaming effects like you would with blazars. And they're quite compact. You know, you don't expect, there's not a lot of travel time for things to get variable and exciting. So we used the vast light curves, so we could track the variability of things over an approximately 2-year timescale. And you can see I've got on the left of my slide here, there's a source that is very much quiescent. It's a very non-varying light curve. And then on the right, we've got something that looks very, very exciting and possibly variable. So we can start to constrain how many of these things are unusual peak spectrum sources. Basically, the summary is most of these things are not unusual. Most of them don't vary very much. The one on the right here is a bit of an outlier. The next thing we can think about is whether there are any interesting gaseous properties of these sources. So as Liz already hinted at, I care a lot about the flash survey and looking for the presence of neutral gas. So the Stripe 82 field that I was focused on actually is now covered by the flash survey. And we have already seen, again, as Liz hinted, that many of the sources in the flash pilot survey tend to be these peak spectrum sources. So here I'm really turning the question on its head and saying, well, how many of all of these peak spectrum sources that we found might have a strong neutral hydrogen detection, which indicates a lot of gas in the system. So when I was doing this work earlier in the year, we only had one flash field covering the full Stripe 82 area, and we had one H1 detection in that field, which is quite nice. As you can see from the inset of the spectrum on the top left of the slide here, it's a pretty convincing line. The SED, unfortunately, though, was quite sparse for its source. So it was relatively bright, about 70 millijansky. So we can certainly detect it now, but in older surveys like NBSS, it was a little bit more difficult, and also the Gleam survey. So we actually have a follow-up program to get some additional flux densities for a lot of these sources with the compact array, to really make use of this combination of spectral line data and broadband continuum surveys and try and get some interesting science out of the detections we're putting there. The third synergy I want to talk about is something a little bit different. So we're actually also using data from IPS. So John Morgan, I think, is in the audience, and he's really, thank you, John. He's really spearheading this project with ASCAP. So interplanetary scintillation, as you may or may not know, is an excellent probe not only of the solar wind, but also of background source structure. So hopefully this shows up a little bit better on the slide. I think it does. So you can actually see on the right of my slide here, there are lots of sources twinkling on the sky. These are not stars. These are radio galaxies twinkling at radio wavelengths. And again, the twinkling here is due to the solar wind. So this is really nice, actually, because we can tell straight away just by looking at the image even that some sources which look compact are probably actually extended. They're the ones highlighted in pink, and that's just because they're not twinkling. The ones that are highlighted in orange are twinkling, and so we can say that they're very, very compact, and we can actually constrain what angular scales they're compact on. So we know that if we see IPS with MWA data, their twinkling means they have an angular scale of about 0.3 arc seconds. And if they're twinkling in ASCAP data up at 1 gigahertz, we can say that they have compact structures on less than about 0.1 arc seconds. So this is a really, really nice, fast, a really cheap way to get measures of the angular structure of these sources without going to all the trouble of getting additional VLBI data. Kind of a first pass on the structure, if you like. So we used, first of all, MWA IPS data, so looking at these 0.3 angular arc second scales. So this was really just 5 minutes on sky with the MWA used to obtain this data. And we could say straight away, just from this 5 minutes of data on sky, that 88% of our sample were at least moderately scintillating, which we interpret as basically saying most of the flux is contained on these 0.3 arcsecond scales, which again is quite nice. That's a nice confirmation that, again, we're looking at sources that are not only peaked, but are compact as you expect a real peak spectrum source. So that's with IPS at MWA frequencies below 200 megahertz. But we also now, thanks to John and Vanessa and the ASCAP operations team, also have IPS data with the ASCAP telescope. So this was actually done with only 2.5 minutes on sky. So now we're really extracting a lot of bang for your buck with observations here. So from this one field, 2.5 minutes on sky, we had 132 sources with IPS signatures, and these were actually worked on by Paris Gordon-Hall, who was a summer student with the ASCAP Flash team and is now just about to start her master's with us, which is very exciting. So she searched through all of these sources and actually found 3 tentative H1 detections from amongst this single field. So that's really exciting for us. 3 is quite a lot for us to see in one single flash field. And it's also exciting because, again, it reiterates this story that we're seeing that lots of our H1 detections also tend to be these very, very compact radio AGN. We then went and looked back at the SEDs of these sources, and we found that 44 of them had ambiguous SEDs. It was a bit hard to tell whether they were peak spectrum sources or not. And this is really where the well-chosen follow-up comes in. So we used 2.5 minutes on sky to identify whether or not these were compacts at 0.1 arcsecond scales. And then we used 6 hours of active time to follow them up and get higher frequency flux density measurements. So this is one of the sources here where we have these higher frequency flux density measurements added to the historical SED. And you can see that they really nicely agree with some of the old measurements, and they confirm that we do actually have, again, a peak spectrum source with, again, a low frequency upturn. So that, as I hinted at before, suggests that maybe we have multiple epochs of emission, and the lower frequencies track some sort of extended emission from a previous epoch of jet activity. And that really nicely agrees with the scintillation indices from IPS. So at 200 megahertz with the MWA, this source was extended. And then if we look at, obviously, the IPS data with ASCAP at 1 gigahertz frequencies, which was what was used to select this source, it is very compact. So that's really nice. We're getting lots of wide area surveys agreeing with each other and all pointing to this singular picture of this source as a compact peak spectrum source that had previous extended emission. So to finish up then, I've worked a lot with lots of wide area surveys over the course of my PhD so far. So a couple of takeaways: it's really nice to have data in an accessible place. Visia is ideal because it has an easy API, but CASDA as well has an easy API. Really anything that makes it easy to query continuum catalogs makes it much easier for scientists to use your data in new and unusual ways that you might not have thought about when you were designing your survey. And the other great thing that I would really like to see more of is survey limits in a machine-readable format. Our modeling is getting much better. It's much easier and less computationally expensive now to incorporate these upper limits into fitting for things like SEDs. So having those, again, easily accessible really makes it possible to extract the most data that we can out of each individual survey. And in terms of what we can do, hopefully, I've shown you that it's possible to combine these surveys in new and exciting ways. We can do multi-band continuum identification and combine that with temporal studies from things like VAST and IPS, and obviously then look at the gaps of things like ASCAP Flash. So I think I'll finish up there. If you have any questions, please feel free to ask or email me, or I am looking for a job, so you could just hire me and then ask me questions all the time. So.
It's a very good idea. Are there any questions for Emily? Yes, Rita, please.
Very interesting result. I'm curious about these upturning spectra. So you said that that's an indication of anodal activity. Are there any, like, what is, do you have an idea about the fraction of these upturning spectra? And is that the only possibility, or are there any other models that explain it?
That's a really great question. So the fraction is actually not something that I've looked at, and it's something I really should, because now we have enough sources, as you can see, that we could do that. In terms of other explanations, so I suppose that there are a couple of subtle complexities here. So the first thing is the Glean data, even with GleanX, which is a bit higher resolution, is still lower resolution than lots of the high frequency surveys. So generally, when we're looking at things at low frequency, we're looking at slightly lower resolution. It is possible that some of the emission we're seeing is just resolved out at higher frequencies. That said, to have such an extreme effect on the flux density where you actually see a turn up and not just a flattening, it would be hard, I think, to resolve out that much flux at high frequencies. So I think in most cases where we actually see an upturn in sort of in the gleam band 100 megahertz, and it's not just flat, it's most likely the case that there is enough flux there that it's not, there's enough flux there, it's not just being resolved out, and it being sort of an older, more extended emission is kind of a natural solution. In terms of other models, that's a really good question. I should probably talk to lots more theorists to get a better idea. But that's kind of our working hypothesis.
Great. Perhaps one more quick question. Yeah, Ron, please. The microphone, please.
Hi, Emily. You showed near the beginning of the talk some variability of these big spectrum sources.
Mm-hmm.
Do you think that could be it could be IPS, but I'm assuming you've excluded that. Can it be interstellar simulation?
That's a really good question, Ron. So we've done, you're correct, it can't be IPS because with the vast data, the IPS signature would be averaged out. In terms of interstellar scintillation, we have done a little bit of work with that, and it's basically quite unlikely. The angular scales that you would need to see that degree of interstellar scintillation are on the order of very small fractions of an arc second. So these things would have to be really, really very compact to see that degree of variability just from interstellar scintillation. Of course, VLBI would help us constrain the angular scales better, but just based on the very extreme small size you would need, it's quite unlikely for it to be ISS.
Great. Thank you very much, Emily. Let's thank Emily again. Okay, so our next presentation is by Vanessa Moss, who's going to tell us about automation of survey telescopes. I'll give you a warning with 3 minutes left before the session.
Don't have slides. Oh,
It should just appear. So big green button.
does that actually work?
Yeah.
Hi, everyone. So I'm sorry, I'm a bit slow. Hold on to your ACLs, you need them. So I'm going to talk to you about about ASCAP. I also have a pretty long slide title. I'm Vanessa Moss. I'm based at CSIRO, which is Australia's National Science Agency, and I oversee the science operations for the ASCAP radio telescope. I realized, so there's actually been a lot of really nice coverage of ASCAP already in this session, and so I'll give you an introduction both to a little bit about ASCAP itself, but also what we're doing with it in terms of the autonomous operation side. So a brief overview of this talk. So like I said, brief introduction, brief mention of surveys, the data flow, and also thinking about, I guess, in the context of this community, what does it look like beyond ASCAP for the facilities of the future and the upgrades we're going to see. So in terms of the introduction, this is just a very high level sort of overview of the parameters of ASCAP, not expecting you to read or digest all these, but if you do want more information, you can go to our website and find out more. Yeah, and also I guess if some people were in the antenna session earlier today, you might have seen Alex talking about the PAF upgrade project, which will hopefully change some of these parameters for the better. In terms of the surveys, so what are the ASCAP surveys? So as you've seen, we actually had 2 really nice talks talking about EMU and Flash, and also mentioning VAST today. I think we have pretty good representation from a lot of the surveys in the audience. So if you have any questions about these surveys, you could find people. But there are 9 survey science projects. They're covering a broad range of different kinds of science. The idea behind these was that with all of the surveys combined, ASCAP would actually help answer and progress a lot of the different kinds of questions. So we have everything from continuum, spectral line, close spectral line, fast transient, slower transient. So there's a lot of different coverage. We also have some observatory projects. And we do have, as of fairly recently, so they're only the last couple of years, guest science time. So if you do have interesting questions that you want to answer with a small amount of time that aren't covered already by the surveys, then that is something that's open every 6 months. And we do have some limited capacity for target of opportunity or technical tests that can help demonstrate new capabilities with ASCAP. And I do want to mention, I know this has been mentioned by Emily as well, but the Rapid ASCAP Continuum Survey, or RACS, this was the first all-sky survey completed by ASCAP, partly demonstrating, but partly also to feed into our global sky model for calibration. And actually, we have passes of RACS at all of the ASCAP bands now, and most of that data, if not all of it, is available on CASDA, the archive. So if, as you can see on the right, this is an image made by Emil Lenk, and it shows how RACS compares to NBSS, which was one of the previous most large wide surveys of radio sources. We actually have much higher resolution. We also have coverage all the way from 700 megahertz up to 1.8 gigahertz. So that's a really useful resource. And just to mention in also the context of this group, so the key capabilities project, which is focusing partly on upgrading ASCAP, improving the software, improving the reliability, but also the path upgrade that I mentioned. So Alex was presenting on behalf of Simon earlier today, and that's an engineering upgrade that we hope will really improve ASCAP's capability to deliver on the surveys. But at the moment, it's for one phased array feed. So to give you a bit of sense of the ASCAP context, so I think a really key factor of this is the remoteness of the site. And I know there's a lot of telescopes represented here that also have the same challenges and the same sort of, we're dealing with, we don't have a 24/7 operations presence, which maybe makes us a little different. So we actually have people go out weekdays. And so from the beginning, it was always designed to be operated remotely, managed remotely, and by I think really importantly, a distributed remote collaborative team. And so that's really influenced. This is both internal within the observatory, so people across the different areas that all collaborate, all across Australia to make ASCAP keep working, but also with members of the community, so the science community and beyond the observatory itself. And so that's a really key aspect of ASCAP, and it's been something that's driven how we approach operations as a whole. So why autonomous scheduling? So this is something I had a talk on Tuesday. So this is the same version of that slide. This is because Ron reminded me that sometimes I think the things that are internalized in my brain aren't also always as super obvious to everyone else. So these are just some of the reasons why in the case of ASCAP, we considered autonomous scheduling as one of the key things we can do to really improve the science operations efficiency of the telescope. Things like balancing all the complex inputs. There's a lot of different constraints to consider at any one time. It's systematic and deterministic. That's a choice that we made. You could choose something that's a little bit less, given the same circumstances, the same input, maybe it makes a different decision each time. We chose something that is rule-based. So we want it to be reproducible in the same kind of inputs. Works 24/7. That is very difficult to achieve with humans, especially at a consistent level of kind of attention. And so it also allows us to redirect human expertise, which is extremely costly in projects, into the things that it's most beneficial from. And it allowed us to consider and develop new modes. So a couple of the ones that are represented here are the SMART survey, which Leora is over there. And if you want to learn more about that, that's to try and survey RFI. So we've done one pass of that, and I guess we'll be working to sort of improve it for future. But also coronal mass ejections, which I know are popular also in this context, allowing us to react and trigger and map these coronal mass ejections in response to inputs from the team. So Sauron is the scheduler. Sarah pointed out that I hadn't made it clear. It also operates. So it doesn't just make the decision, it also then communicates to the telescope and actually executes things. So there's an underlying automation layer that Craig Haskins developed. I guess this was good in the sense that ASCAP was always designed to be sort of, even though there's a clickable interface that just communicates to a lower base level, and then Sauron could kind of sit on top and talk to Craig's layer in between. So that was a really important aspect. We didn't have to, even though Sauron wasn't planned from the start, we didn't have to completely reinvent the system, but we could work with it and just sort of integrate with those interfaces that were flexible enough to do so. So Christmas 2020 was the very first time we ever tested it. If you want to know more, I skipped that slide because of time, but basically we went from 50%, I think it was 50% observing efficiency, so within a given day, to 70% just in that one jump. And we also saw a jump based on partly Sauron, but partly consolidation, from 70% to 95% success rate. So that was the kind of biggest gain we got, but then since then it's kind of been at a pretty high level. And so you can see this in this plot here. I haven't labeled all of the different sections, but this was combining pilot surveys, which were our first sort of foray into how does ASCAP operate, into where we are now, which is full survey operations. The middle, I guess, does this work? Oh, it does. Okay, so that little spike there, that was the first time we ever used Sauron. That was before, where it was semi-automatic, but quite manual with a lot of kind of errors. So, you want this green line to be close to 1, and you want this to be close to 1 too. And then as you see now, we're much higher in our overall kind of efficiency. If we look back to the history of ASCAP from when it first started observing, you can see we're on a good track. And besides, those dips, they're most we can probably trace, especially the significant ones, we can trace back to significant interruptions that are well beyond the capability of Sauron to do anything about. But it does mean when we can operate without interruption, then we can kind of make up for that time. In terms of what happens after the data is observed, so we have data flow to PAWSI. This is our ASCAP buffer system. It should be Ruby Payne Scott, but at some point, I think the processing wanted Payne as a bigger partition, so now it's Ruby Scott Payne. But anyway, it's fine. Scott and Payne are both used for processing now, and it's a good chance to mention Ruby, who, if you don't know about, I highly encourage you to research her. But she was the first female radio astronomer and also came from Sydney. And so for a slight diversion, because this was mentioned, this is the first flagship URSI since 1952. That was also the last conference that Ruby, well, maybe first even, but Ruby was at that conference, and this was at the University of Sydney. And so you can see her in, oh no, okay. But anyway, this is AI color version, which was kind of cool. Didn't like this guy. And I don't know what happened to his suit. Anyway, so yeah, so Ruby was there. That was actually, unfortunately, the end of her career. It's a very interesting story. I highly recommend. Talk to Ron and others if you want to find out more. And there's a Ruby ferry. So if you're a visitor to Sydney and you're ferrying at any point, keep an eye out for the Ruby Payne Scott ferry. I think it'll take you to Parramatta, which maybe you want to go to, but just also be on the Ruby ferry. Anyway, so that's a slight diversion on Ruby, and happy to talk to you more about Ruby at some point. So in terms of processing, I'm not going to say a whole lot about that other than there's ASCAP soft, which was custom developed to process the data and calibrate it. It's very complex data, as you probably got a sense from the talks earlier today. It runs on the PAWSI supercomputing infrastructure, specifically Photonics. That's been something that's evolved over time as upgrades happen. The data, once it's processed, is sent to CASDA for the science teams to access. Again, similarly to what we're doing in science operations, data operations has been moving towards more and more automated with processing manager and C-Link acting as the interface there to trigger observations and make sure everything's processed correctly. And we're still working for better linking of observations and processing. So for example, do we need to process everything, or can we make a decision earlier on to not process a particular bit of data? And so for more on that, see Matt's talk on Friday. Collaborative intelligence, I do want to briefly mention this. That sort of feeds into that, like how do we more automatically detect it, but then feed that information back into what essentially still like are human systems, like there's still humans overseeing the whole process. So the collaborative intelligence or Syntel project, something that was sitting in CSIRO. We've looked mainly at using hardware monitoring data, detecting outliers there, but also then raw data diagnostics and brokerage, which is the hardest one because that's the human one. How do you get all of these systems to work together and synthesize all the information? And then what do humans do with it? Is it interactive? Is it collaborative? So these are just a few examples of the kind of projects we have. So on the top right, it's that's GILA, which actually, so it's based on raw data plots we have, characterizing training based on known issues we have, and then detecting them, and it actually has a pretty good rate. What we still have to do with this is then say, all right, which ones do we trust? How much do we trust them? And can we automatically feed flagging back into the pipeline based on those, as well as looking at historical events, so big disruptions, and how could we predict them in advance? Could we do something about them sooner? Often not, because a lot of the indicators are quite severe, but we're still looking at more of the subtle ones. And then the whole, how do humans interact with AI, which is a really interesting thing, but also really difficult. So beyond ASCAP, so I wanted to briefly mention DSA 2000. This is a slide borrowed from Francois. So in case you missed any of the DSA talk so far, this is what DSA is planned to be right now. It's going to be in Spring Valley. It's going to be a really immense, really cool collection of dishes, many dishes. And in some ways, like a kind of northern cousin to ASCAP. So a lot of the same questions we've dealt with ASCAP, thinking about surveys, thinking about efficiency, how do we operate complex things, how do we operate remote, apply really directly to the DSA case. So it's really exciting to be working with the DSA team and thinking about what we've learned from ASCAP and what applies here. And there are a few DSA people around. You can see Francois over there. So if you want to find Francois, Vikram, or Vinan and at the conference, then you can ask them all of your DSA 2000 questions. So in the context of DSA, what I'm working on via CSIRO, we have a collaboration, is the observation planner. This is slightly bigger than just scheduling, but it has to do essentially with how do we plan the observations, how do we execute them. And so these are some of the key things we're thinking about right now, which is, based on our lessons learned from ASCAP, what do we feed into DSA? How can we do better? And we already have, I think in Francois' talk, he mentioned the MVP, so the minimum viable product. So as part of the test array, we have a very basic working version of OPL, which is capable of talking to the MNC interface. And so that's something we can build on. It's already, thanks to Kevin and Daniel especially, but others, it's like improving a lot on what we did for Sauron, which was like kind of as we transition to operations, how do we make, what do we do? How do we make this more efficient? In this case, before we even start building the telescope, we have the chance to say, all right, well, how do we do this better? How do we design this? So that's pretty cool. And it also feeds into how DSA eventually will be operated. Complex system debugging. This is an ongoing thing. I know many people in the room, depending on your expertise, are very familiar with ASCAP. It has three, we have three Vs here. Unfortunately, veracity does come in at times, but so pretty much all four Vs. So there's a lot of there's a lot of expertise. I wouldn't say we've perfected this. It's something we're still optimizing. As we were transitioning to full surveys, we did have to balance new features versus kind of operating, continuing. Now I would say we're a little bit more in a stable state, but we still do want to make the system better. So that's something we found automation has actually been quite critical there, as well as being able to visualize things. And then trying to balance how much can we do without human input, how much can we automate. Operability for us, the transition from experimental early science beta observations towards full surveys was a process, and the pilot surveys as well as the full survey trial really helped fill that gap. There wasn't a magic switch. I think every telescope that's ever been commissioned has gone through this, but I think it makes it really important to assume that it's not just a switch. You have to go through this process, and you are going to have to sometimes significantly improve the system that you thought you might use for operations. This one's a fun one. Hello, survey teams. Realistic versus ideal operations, working with people to figure out what is actually critical for the science, what is, how much do you need to avoid the sun? When's data good enough? How do we predict the future? Think a lot about predicting the future lately. How autonomous can we make ASCAP, as well as like human effort invested? Because like I said, it's one of the big costs. So the less we can use it, the better. So these are all things that, I think definitely we haven't perfected, but like thinking about how do we do this for the next generation of facilities is really important. And so just to borrow a slide from my Tuesday talk, as well as all the engineering upgrades, as well as all the innovative new instruments, we really need to think about the holistic view, how we bring all of that together, and how we can, from my perspective, automate as much as possible, sometimes with AI, sometimes just with a good Python script, in terms of which facilities best benefit from these sort of approaches. So in summary, our overall takeaways on ASCAP are, before even the full survey started, we were able to work with teams and demonstrate high quality science output. You saw Liz going back to beta observations to detect H1. And the system since then has come a really long way, I guess, in 10 years, in terms of being really operational, being able to conduct survey observations at a high rate. There are still challenges, we can talk about those. But automation has been a key thing in improving our efficiency, especially in terms of being able to carry out observations at all times a day. A lot of the lessons do translate to the next generation of facilities, so please come talk to me. And we are thinking also, as been mentioned a couple of times, about the future upgrade pathways for ASCAP. This will be driven by what creative ideas people have, but also what the community is going to need for science. So yeah, contact you, many of the people at CSIRO if you're interested. Thanks.
Thank you, Vanessa. Any questions? Yes. Am I going to the microphone? Hey,
thank you. I know that this is an ASCAP sort of Sauron, right? It's an ASCAP specific thing. As you develop the messaging, communication protocols, you're also executing observations on your telescope. Have you put much thought, or do you intend to, for how that can be agnostic, like for other telescopes? Can I use Sauron?
No, it's a really good question. We should talk more. I mean, I think so. Part of that has been when it was originally done, it was an experiment. It was like, no, it hadn't really been done before to this level, so it could have failed. And so we thought that was in 2020 or so. We went with it. We thought, okay, we'll try it. If it doesn't work out, we have humans. It's fine. When it did work out, like you say, it was sort of designed a little bit custom to ASCAP. But actually, the process of designing the DSA version, which we're calling VADA, I draw on other people's Lord of the Rings knowledge, but VADA is pretty cool. And also the opposite of Sauron, maybe. But VADA actually is more of that agnostic thing. So in the terms, so already I guess maybe this is something we can talk like with DSA, but we are abstracting it more. So a lot of the more specific stuff to ASCAP is already gone in the DSA version, and I think that's sort of the process. So we definitely would like to look at more abstraction. I have to write the paper. That's a priority. But yeah, no, I think definitely it'd be cool to talk more about context you might apply it, because we're definitely keen to do that.
Cool. Another question? Yes.
I wanted to ask more from a pure software perspective. I'm one appreciating how small your team is. Very foreign to me coming from Soraya, where the people I meet every day, I think, are they visiting or do they work here? Genuinely don't know. So from your side on the software, do you prioritize enterprise level software? So do you have support outside of your little organization, or are you open source all the time? Move fast, move quickly.
That's a really good question, and I wish Steve Ward was here to kind of give his take on this. But I think it's a bit of a mix. I think there has in Cyro, there's been a push to where we do need to go to like things we can't develop ourselves using open source. So I didn't get to talk about it in detail, but things like CSS, Control System Studio, or Grafana, or like InfluxDB, and a lot of DSA is making some choices similar. So I think there has been a generally, if we're using, we don't pay for things that require big, heavy subscriptions, and we try to develop it ourselves if we can. But in terms of the scale, like I don't know, there's various things. So when it comes to the control system of the telescope, that's something that has to operate all the time. So there's more emphasis on stability and like making sure that the releases are really, if we change anything, not perfect, but there. And then if it's something smaller, then there's more flexibility. So I would guess, yeah, I think actually it was interesting. I should talk to people, but like Alma, I think that it was like 110 people on site each day. So many. Like I was like, wow. So I'm really interested to know more about that because yeah, we're lucky to have maybe like 5 people on site each week for ASCAP, for ASCAP. And so like it's interesting to see how different facilities are approaching it, and where we can learn from each other in terms of this is needed, this would help our efficiency, or maybe we could change that. So yeah, I think more collaboration on that front would be good. We should talk about Meerkat.
Great. Okay. Thank you very much, Vanessa. It's cool. I'll have to move on, but let's thank Vanessa again, please. Okay, great. So our next speaker is Keith Bannister. You're the next contestant. Keith will be talking about aperture array technologies.
Okay. It's 20, right?
Yes.
And what's my button here? This one. Okay, good. All right, thanks everybody. So my name is Keith Bannister. I'm the Chief Technologist at the CSIRO Australia Telescope National Facility. Today I'll just give you some updates on what we've been thinking about for a potential future mid-frequency aperture array and other technologies we've been developing to try and address what we might build in the future. I just wanted to make the point that aperture arrays are not my idea. I really like them. I'm enthusiastic about them, but it might sound like it's, I think kind of it's all like an idea that I had, but I'm just trying to acknowledge up front that it really has been a long road up to getting up to this point. And a lot of people have done a huge amount of work, I think, early on, especially in the SKA project, and I'd like to call that especially Embrace, which was a completely revolutionary telescope, I think, at the time, far ahead of its time. So anyway, we're basically thinking of reprising a lot of that work, bringing it up to date with the modern technology. So this is just a taster, I guess. Come and talk to me if you want to know a little bit more, but I'll just talk through some of the projects and some of the technology we've been looking at, and maybe try and motivate it a bit with some of the science you might do at the end. So Lambda is already, I think, been talked a bit about already. So Lambda is basically the idea is some long baselines for to complement SKA low. So we would be putting them, I don't know how well that's come out actually, basically around a few sites around Australia. So patches that are similar to an SKA low station or order 256 antennas. We'd probably like to make them into all-sky monitors as well. So because they wouldn't be being used all the time for VLBI purposes. The challenge there is that you have to handle a more severe RFI environment than the SKA site, which is obviously very good. At the moment, it's funded to build a small station in Narrabri, and we'll hopefully build that out to a full complement soon. Another project that we've been looking at is called the Lunar Path. So the idea here was motivated by a question from Breakthrough Listen, which was, can you build a probe that goes to the far side of the moon where there's no RFI and look for, do a probe for a SETI, basically survey, and measure the voltages of the universe before they get contaminated by the RFI from colonization of the far side of the moon. The challenge there, which actually, I mean, whether or not you think that's a good idea, I'll leave up to you. But it really left us with an interesting technological question, which is can you build a decent radio telescope for less than 100 watts? And that's actually a really interesting problem to try and solve. And ultimately, any type of aperture array you're going to build is going to run into power constraints at some point. So trying to do it on the far side of the moon is just as hard as trying to do it on the ground. Well, probably even harder. So if you can do the moon thing, or you even shoot for the moon, then maybe you'll get close. So we've been looking at a few technologies to do that. Our postdoc Brian Degama has actually been looking at using FPGAs to do 1-bit analog sampling. They're using the digital pin on an FPGA to do 1-bit analog sampling. And then you can do all of your elements in a phased array feed, for example, in a single chip without having to do spend too much power. So this was this is picture on the right is an example of how that might work. I was at an FRB conference and Stefan said Stefan, I forgot his last name now, wanted more FRBs than galaxies. So I thought, okay, well, that sounded like fun. So we've kicked off this concept we call CASADA, which stands for Coherent All Sky All the Time Array. The idea here is barbecues as far as the eye can see, which I think has already been shown previously. But the antennas probably won't look like this in practice. But the idea is really to try and bring back this idea of an all sky monitor and a frequency range. We've been looking at 400 to 800 recently, but actually there might be a second array that goes 800 to 1.4. I'll talk a little bit later about the science at 1.4 gigahertz is actually pretty compelling. You can get many rotation curves. Interestingly, so for something that has the same scale as SKA low, 130,000 dipoles, that has the sensitivity of about 2 or 3 Parkes, the Parkes radio telescope, but with 10,000 times the field of view. So it's not insane. Like it's actually, if you build something like this in 10 years' time, I mean, we're already building SKA low. We know how to build 130,000 dipoles, or we will by then. So, and this thing is a lot smaller. Like in terms of, you can build instead of having one dipole that one antenna that you might fabricate and then put out in the field, you can put something on the back of a truck that might hold 16 antennas, for example. And so the fact that it's shrunk just because of the wavelength is a bit shorter means the whole thing is actually a lot more practical than you might really imagine. So the science here is, again, I'll talk a bit about more later on, FRBs, magnetars, H1, and we're talking with a few other institutes to try and make a loose collaboration. And I'll show you a few sort of things we're looking at here. One of the examples is fast radio bursts. So these are bursts of radio waves come from far away in the universe. And we're now in the position where, especially there's a few telescopes around the world that are detecting them at a fairly high rate, a few a day or a few a month, and localizing them to a galaxy. So that kind of whole process is now pretty well established. But to really get to the next few orders of magnitude, you want to be finding of order 10 or 20, 50 a day even. And you want to have arc-second localizations of them. And really, another thing that's really helpful with fast radio bursts is, the problem with fast radio bursts is that they come from so damn far away that if you get a location, a galaxy, it's very difficult to investigate the actual environment that the FRB was emitted from. And there's a very small number of exceptions to that. And where you do have a good localization to, say, a globular cluster, for example, in one case, it gives you a huge amount of information that is just very difficult to get any other way. So really what you want is more nearby FRBs that are the easy ones to study. So the way to do that is, ironically, to make a less sensitive telescope with a wider field of view. And so you can actually see these nearby FRBs. You've got a better chance of finding the ones that are close. And you can do a little bit more actual investigations of those individual FRBs, as well as actually, when you have a very high density of FRBs in the nearby universe, there's some hope that you could actually make a nearby map of all the kind of baryons, or the cosmic web in the nearby universe in that kind of dispersion measure space. So nevertheless, with, say, a small number of antennas I've got on the top there, 256 antennas, you might get out to, say, redshift, 0.1, 0.2, maybe up to 0.5, if you're lucky. And those will be mostly nearby FRBs. And then on that bottom thing, obviously, if you end up with 64,000 antennas, you'd end up with something like the Park sensitivity or around about, and that still sees FRBs out to Redshift 2. There's a couple of other things I've just mentioned there, and in particular I'm kind of excited about the EMGW stuff. So neutron star mergers detected by LIGO. You don't see them until like LIGO gets maybe a minute's worth of notice, and they don't really know where in the sky they are. So if you're monitoring the whole sky when they happen, then straight away you can put constraints on any neutron star, any emission, prompt emission from neutron star mergers. Some of the technology we've been looking at, so we've just been developing some antennas, and well, we've been doing this for several years now. So Ron mentioned this idea called CASPA, and I think he might have given a talk about it. I wasn't able to make it, but this is the CryoPath, which is one of my favorite instruments ever. It just looks so beautiful. And in principle, you could just put it on the ground and look it up, get it to look up at the sky. This is a great machine and very sensitive, but it's just using a lot of it's using a lot of elements to not have a very high collecting area. So you can see the size of this thing is, 1.5 by 1.5 meters around figures. And so, you've got 200 odd elements there. And so you've spent a lot of digital system just trying to collect photons from 2.5 meters. On the other hand, it's up to 2 gigahertz, which is something that's unique. But we've got some beautiful system temperature measurements here, which is kind of, spectacular, really. So it's, that would be quite a capable instrument if you just put it on the ground. Unfortunately, all our pulsar astronomers want to put it on the dish, and that was what it was designed for, and that's where it will stay. So back to the drawing board for that. But it's an impressive piece of kit. I think there's more up-to-date information there. But yes, Ron was basically just let us do some science with this thing. And he talked about this CASPA concept where you could find some really interesting sort of FRBs very straightforwardly, actually, with something like this. I'll just skip through here. We've just been working on this for the Casada concept. We've been looking for playing with this butterfly antenna. So Maral Ansari gave a talk earlier about a version 1 of this concept of an antenna. She wasn't able to get all the way through that talk to get to this newer version. So this was it being tested out at Marsfield, and the idea here is it's just a pretty simple dipole really, but it's got an active balanced LNA in the top. So basically, it's the LNA is all built into the top, and then you can take coax out the bottom and then digitize that. So that's in testing at the moment. We've got a version 2 that literally arrives in the country this week. So hopefully we can have that populated and tested and have some patterns soon. But that's got like I said, that's got a built-in LNA. There's an updated version of the TSYS. I'm not sure I've got that, unfortunately. The TSYS was more like 20 Kelvin. So that thing on the bottom right's not right. But the TSYS was pretty good for a commercial transistor, a bit under 20 Kelvin. LNA testing was fun. So I showed this to a few students, and you get to play with liquid nitrogen and dress up in funny costumes. And the key point here was we chose for the antenna gain pattern to, it's really tempting to go just as big a possible gain, like a bigger possible field of view as you can. I mean, you're trying to build an aperture array that's got a huge field of view. And so it's tempting just to go all out and just try and cover the whole sky. With hindsight, we decided not to go all out on the grounds that there's RFI often coming from the horizon. So we decided that if we have a little bit of gain pointing up, we can try and null out some of the RFI on the horizon and make our lives a little bit easier from that point of view. So that antenna simulation shows you that you get about a 4,000 square degree field of view, which is still appreciable, a gain of 9 dBi, and then you'll and it's unfortunately the beam's a little bit squinted, so it's a bit elongated in one direction, but I don't think that'd be too much of an issue. And so for 256 antennas, you get this kind of, I've just done a sky model from the global sky model if you had different receiver temperatures. And you can see that if you get around a 20 Kelvin system temperature, receiver temperature, then the sweet spot in terms of SEFD is at around 300 megahertz. But that antenna is going to be 300 to 500 or 350 to 650. And the reason for that is just the FRB scattering actually starts to dominate. If you're trying to look for FRBs, you don't want to go too low because there's probably going to be fewer FRBs there. So the array simulations are ongoing. They're looking really good, but we haven't quite got there yet. So we've been also thinking about digitizing. So in the kind of cost breakdown, actually the antenna is amazingly cheap in comparison with the things that it's attached to. And so the next step was really to try and work out how to reduce the cost of digitization. And there's a few different ways of doing this. So you can do RF over fiber, which is that top thing. You transport your data over analog over fiber, and then you digitize somewhere in a box. The second version is where you have an ADC and you have put that in the field. So digitize in the field, put that inside a nice, well enclosed, shielded box, and then you try and decode that. Thanks later on. And then the final version is you put everything out in the field, and then you basically have commercial off-the-shelf stuff in the box in a data center. So we've basically got to we're shooting for something like $200 per input, and we're getting pretty close to that number at the moment with the second architecture that I showed you. And so that's looking pretty promising, and we'll deploy that on the Lambda array shortly. So here's a picture of that ADC, and it goes inside that box there. And those boxes are looking pretty good, and so far we've measured them and they're completely RFI. There's not a lot of RFI coming out of them at all, so they should be good to go out and put on the ground next to an antenna. This is the box that actually receives all that data, and that's just off the shelf, mostly off the shelf FPGAs with these expansion cards, and then in a nice 1U box. We would like to build an ASIC to do this job. So basically this ASIC would be out in the field with the digitizers, and it would be digitization like analog on the input and then Ethernet on the output. And then basically you'd have a nice signal chain that would be very low power, low cost, and also completely, off the shelf compatible in terms of what you have inside the main data center. So it would go straight into a commercial switch and then you'd be done. So that's something that we're working on, and hopefully we'll have some prototypes in the next maybe 12 months. So we've been looking at EPIC, and so David and Mithya have been looking at this, and this is an FPGA implementation of EPIC, which is a beamforming algorithm, and this gets you something like 7 cents per antenna per megahertz, which is cheap because you've divided by some big numbers there, but still you probably want another order of magnitude, I think, for this sort of processing. But it gives you an idea that we're thinking about this, and certainly we're building, medium-sized arrays will have options. We've been looking at analog beamforming. So this is some work that's been done by Paul Roberts. And you can see this is a Rotman lens. So basically you feed 8 antennas in on the right, and then you get 8 beams out on the left. And this is a completely passive device, and will form beams on the sky. If you want to do an 8x8 array, you'll need 8 of these, and then you connect them to 8 other copies of it, and then you basically do a 2-dimensional beam forming thing completely passively. So this is a good example of how you might. This was driven actually by that LunaPath idea to make a really completely passive beamformer. I've been working on a lot of algorithms, so I've been working with my postdoc Vivek on a thing called ESAM, which is a de-dispersion algorithm, and some beam SKLO calibration. I guess the point I wanted to make here, and I'm probably running out of time, I'm sorry, but the science is really solid. I think we'll just do a bit more work on the science case, but there's a lot of interest and a lot of groups around the world looking at this sort of concepts. When you think really ambitiously and you start to think about where you go here with this stuff, it's actually, even for a survey telescope, it's 10 times more cost effective than DSA 2000, which is already 10 or 100 times more cost effective than SKA for survey speed per dollar. So, for example, 16,000 elements of a Casada array would have the same survey speed as SKA mid, and we do it for, I don't know, maybe $20 million, $30 million. So, as you grow that, obviously, the size of the collecting area goes as, for a normal dish goes as d to the 2.7, but sorry, the cost of a dish goes as d to the 2.7, but the cost of these elements goes as just d squared. And so, you're always kind of going to win with these aperture arrays, amazingly. Anyway, so we'll see if we can develop a technology where those coefficients actually get to make some sort of sense before, in that scaling relations. We still need to demonstrate that $1,000 per antenna or less is achievable, and that's something that we're trying to do over the next few months or years, really. But it's also a hard work because you're really working on very low cost hardware, and so you have to be careful not to spend all your money on NRE, because it's very easy to spend a lot of money on NRE and not a lot on hardware in the end. I'm going to run through here, but yeah, Vika and I put together a plan for world domination. So I think in the next few years, there's a few groups around the world doing small demonstrator arrays. And then ideally, we'd be ready to do a 16,000 element array in, say, 2030. And then we'd have maybe 130,000 elements in 2035, and then a few of those around the world in 2040. Okay, I'm just going to leave it there. Thank you.
Thanks, Keith. Any questions for Keith? Yes, please. If you wouldn't mind going to the microphone there, that'd be great.
Just a quick question. Oh, sorry, presentation. Just a quick question for the start is that you wanted to place some stuff on the far side of the moon, which obviously would reduce the RFI, which is obviously amazing. But out of curiosity, what RFI signals would you still possibly see on the far side of the moon? And will you have some problems with the moon's orbit and how sometimes it'll be directly facing the sun?
Yeah, so you do have the trouble. The sun does come into your field of view, and you have to think about that. Aperture arrays don't probably handle the sun especially well, so there's certainly algorithms you do to employ to try and improve that sort of stuff. Ultimately, yeah, radio astronomy, even though we like to think of it as a 24/7 operation, it is better still at night. Yeah. In terms of other RFI, obviously there's the device you bring with you, and we're getting pretty good at actually shielding our own stuff when we try. So there's lots of, digitizing in the field is not new. Like Meerkat has digitization right in the focus, and that right near the focus, and that works really well. So that's been done. But the other thing is there's orbiters and a few other people wanting to go to the far side of the moon for their own reasons, and they'll bring their own equipment, and we don't have much control over that. So to some extent, there's some urgency to try and do this sooner rather than later, because it might not be as pristine as you'd like for very long.
Yes, I talked a little bit in my talk yesterday, but again, not details. The lunar, in the ITU, the International Telecommunication Union that does all the communication, has been for more than 50 years, never before, and a recommendation about the moon, doing astronomy from there. And they're suggesting things like, we put all the communications about 2 gigahertz and leave the spectrum below 2 gigahertz just to do astronomy. And it has been always not possible, but now with all the missions going, it started taking up there. So there's an organization called SFCG, Space Frequency Coordination Group, which is all the space agencies get together a couple of times a year. And we're invited to those. And we're working very hard to limit the communications and all the other things to specific bands, which can allocate and leave the rest of the spectrum as possible. It is a hard task, but people working in the ITU has got a lot of work and an agenda item in the next World Radio Communications Conference. So it is still hope.
Certainly, I think from my experience up to this point is that the intended emissions are part of the problem, but the unintended emissions are also a problem.
Okay, thank you very much, Keith. I'm sure we could have lots more questions, but let's thank Keith again. And our last presentation for this session, Simon Johnston will tell us why it's also a good idea to put the cryopath in the dish as well.
How do I move forward? Just the green button.
Yeah, the green button. Yep.
Okay, good morning, everybody. My name is Simon Johnston. I'm working for the CSIRO. I'm the astronomer at the kind of pointy end of the cryopath, and it's been a huge engineering effort to get us as far. So I'd like to thank all the engineers for their very hard work over the last few years in getting us here. So what is the cryopath? Keith said it's his favorite looking instrument, and that's certainly true. And if you go outside the door out there, you can see some examples of it on the desk. So it's a phased array feed with 98 dual linear polarized elements, and you can see them here, the so-called rocket path, because they look like rockets. And we're going to mount it at the prime focus of Marianne, which is the Parkes Radio Telescope, some 350 kilometers west of here. And we've cryogenically cooled it, and we want to get the SSIS around 30 Janskis or so, and the TSIS somewhat less than 20K. So the frequency range from 700 megahertz up to nearly 2 gigahertz. We've had to divide that into two bands, mostly because of the RFI at the lower frequencies. So there's two separate bands, 700 to 1100 megahertz and 1100 to 1950 megahertz. And you can have a process bandwidth of 614 megahertz. So you can do the whole of the lower band in one hit and nearly all of the higher band in one go. So what this does for you is it makes 72 beams on the sky. Rather than having a single pixel feed where you've only got one beam, now you've got this multiplied by 72. And the beams on the sky are all formed in an FPGA beamformer. The FPGAs also produce the science-ready products. The data then flows into the GPUs, and there's a lot of flexibility in the GPUs to do what you like with the science modes, and it'll produce science-ready data products for you. And we're planning also, CSIRO has a big data archive. These data will all flow into the data archive for public consumption. So why are we doing all of this? Well, survey speed is a key metric for many science applications. And so survey speed, for high survey speed, you need a big collecting area, you need a low system temperature, and you need a very large field of view. And so the cryopath ticks all those boxes. The Parkes telescope is a 64-meter telescope, so it has a very large collecting area. We've cryogenically cooled it in order to reduce the T-cis as low as possible. And so putting those things together, the field of view is 3 times the old Parkes multibeam, and it's got twice the frequency coverage. But the thing to keep in mind is it's 50 times the field of view of a single pixel. Furthermore, the old multibeam system was a horn system, and there's a lot of advantages of phased array feeds over horns. Firstly, you can uniformly sample the sky rather than having holes where the horns are, where the horns aren't. And it was very difficult to tessellate the sky with the multibeam. It'll be much simpler to do large area surveys with the phased array feed. And not only that, you can use the phased array feed to do things like reduce your baseline ripple. There's the potential for blanking out RFI, for example, and there's a whole lot of other interesting things you can do with phased array feeds that, of course, you can't do with horn. So this is just what the beam footprints may look like. It's about a 2 square degree field of view. The field of view doesn't depend too strongly on frequency. It's pretty much frequency independent. You can have 72 beams and you can arrange them in various patterns. Oh, so the thing to note here is that the sky is very nicely Nyquist sampled. You have uniform sensitivity over a large area. So you don't have holes in your sensitivity as you would with a multibeam, for example. The RFI environment at Parkes is not great. These are the top 2 plots basically cover the bands of the cryopath, and you can see that below about 1050 or 1100 megahertz, things are pretty evil. So that's why we've had to put a notch filter in at around 1050 and split the band up into two parts. So that's one thing to keep in mind, and one thing we're going to have to do quite a lot of mitigating to do the science that we want to do. So I want to skim through the science in the time I've got. There's quite a lot you can do. Single dish, wide field of view. I'll go through transients and fast radio bursts, pulsar SETI, H1 and OH. We'll really just skip through these very briefly. So firstly, on SETI, the Breakthrough Listen has had a project on the Parkes telescope to carry out SETI research since 2016, and they've used the multibeam. They're currently using the wideband system that we've got, and of course, they're very interested to use the cryopath. They want to target both nearby stars and exoplanets in targeted searches, and of course, carry out untargeted searches of the galactic plane and the galactic center with the cryopath. Breakthrough Listen themselves siphon off the data into their own GPU cluster, where they have very fine hertz frequency resolution to look for Doppler shifts of intelligent lines. So that's one of the things that's planned. I'll talk a little bit about neutral hydrogen H1. You've heard a couple of talks about that this morning. So the cosmic microwave background shows the imprint of the Big Bang on the very early universe at very large redshifts. And in a similar fashion, H1 can be used to trace the matter in the universe over a range of redshifts because it's a spectral line. But the problem is that H1 is super weak. So Elizabeth told you this morning that it's very difficult to see H1 in emission above a Z of about 0.2. And that, of course, is correct. But one of the ways to get around that is to observe 1,000 galaxies at once in your beam and sum those galaxies together. And so that's the idea here for this experiment. We want to look at H1 in emission at a redshift of 1 in intensity mapping. And so what you do is you point your cryopath at an area of sky which has been done in the optical. You know the redshifts of all the galaxies, and you sum and add the data together in a stacking kind of fashion to try and see the H1. Let's go back one page. And this was done in 2016 with an uncooled path that was on the telescope for about 6 months. And Jacinta Del Hayes has a detection here of a whole bunch of stacked galaxies. You can see on the plot on the bottom, this is an example of the baseline ripple that was present in the multi-beam compared to what was present in the 2016 version of the path that we had. And you can see that really nasty ripple, which is hiding your H1 signal, has largely gone away. But there are many challenges at a redshift of 1, which is 700 megahertz. The RFI is particularly bad, and we're going to have to really do quite a lot of work to get rid of the RFI. The other big plus with the cryopath is a survey for OH. So with the old multi-beam, it didn't cover the OH frequencies. So the previous Parkes OH survey was done with a single pixel feed. It took 2,000 hours. This is the flash survey. It did 12 minutes per pointing. And with the cryopath, you can basically do this 40 to 50 times faster. And so you could knock this off in 50 hours. So why is this interesting? You're looking at the hyperfine transitions of the OH molecule. And what you would like to do is see discover the masers and monitor their variability, but also to look at the diffuse OH in our galaxy, because that's a tracer of the molecular cloud formation, interstellar medium evolution, and the baryonic mass content of our galaxy. So this is a map of what's been done before. As I said to you, the flash survey only covered a very small region, and so that you can see these little red squares are what's kind of previously been done, plus the blue survey towards the galactic center. But with the cryopath, we'll be able to cover this whole area in a finite time. And the reason you need single dishes, of course, the ASCAP telescope is also doing OH survey, but in order to find the very diffuse gas, you really need these zero spacings that a big dish can provide you. So interferometers are great, but you can't map the extended emission so well, and you can certainly combine the zero spacings with Parkes with the ASCAP data. And of course, the diffuse OH is rather weak, so you need deep observations, and cryopath survey speed means that you can cover a decent area of a galaxy in a good time. The Parkes telescope is well known for its pulsar surveys. It's basically been doing pulsar surveys almost continuously since the 1980s. There are 4,000 pulsars known, nearly half of them are Parkes discoveries. And the FAST telescope is really finding a lot of pulsars recently, and also the Meerkat telescope. Why do we want to find more? Well, that's because pulsars are the greatest thing in the universe, and you can never have enough of them. But really, it's because there's a lot of really good physics that you can do with pulsars. There's the equation of state of matter by understanding the interior of neutron stars. There's the time standard. They're more accurate than atomic clocks. There's gravitational waves, which is the stochastic background of supermassive binary black holes in the early universe. And they have super strong magnetic fields and super dense matter that you can't reproduce in the lab. So if you want to do your experiments, you have got to look at pulsars. Blind surveys, of course, turn up gems such as the double pulsar and indeed fast radio bursts. And we would really like to find a pulsar in orbit around a black hole. That's the next big thing. But where best to look? There's the galactic plane itself, because pulsars are basically concentrated in the galactic plane, at least the young ones. But there's the whole sky if you want to look at the nearby population, for example. So I just wanted to give you one example of a pulsar survey that we could do. The Fermi gamma ray satellite has detected an excess of gamma rays towards the galactic center, and it's really not clear what this is. The two models for it are dark matter annihilation of exotic particles, or far more likely, in my opinion, a whole bunch of millisecond pulsars. But current pulsar surveys are really not capable of detecting millisecond pulsars at the distance of the galactic center. But a deep survey with the cryopath can cover this sort of area very deeply, and we could potentially discover more than 100 millisecond pulsars, which would then be timed in the future with the SKA, and hopefully solve this decade-old mystery of what the gamma ray excess in the galactic center is. Fast radio bursts, the progenitors of the fast radio bursts are still unknown. Their use for cosmology is only kind of slowly emerging. With the cryopath, in principle, we can do commensal searches all the time on top of extragalactic H1 surveys, on top of other pulsar and OH surveys. We have the ability to capture a transient buffer. So when a trigger goes off, we can capture very high voltage, time resolution, and polarization. There's a possibility of doing VLBI in real time for some of this. Of course, we need another dish somewhere that's kind of tracking the Parkes telescope. But that's something we're looking into, and allows us to test new search algorithms and technical developments. So the rates of the Parkes telescope are on ASCAP, they're finding about one a week. With the Parkes multibeam survey, we found about one a week. With the Parkes cryopath, you could find one a day if you really had 24/7 operations. And that compares to CHIME, it's currently finding about 3 per day. But with the Parkes telescope is a much bigger collecting area than CHIME, and so Parkes typically will find high dispersion measure, high distance pulsars. So if you're interested in how FRBs track with redshift, you need to find the high DM ones. The localizations will be good, but they're not anywhere near good enough to do optical, to find the optical counterpart. And as I said, there's a voltage buffer, so we'll be able to do high time resolution. Am I good for time? 3 minutes, okay. Okay, so that's just a quick romp through the main science things that we're planning to do with the cryopath. I just wanted to show you that the cryopath is kind of doing good things. Here's some commissioning results. This is from Mr. Saverly Smith. This is the LMC, a Large Magellanic Cloud mapped in H1. And we compared this to the old map with the multibeam. This was done with 50 pointings of the cryopath, so that's 2,000 beams on the sky, kind of knocked off in a couple of hours of observing. Of course, the H1 and the LMC is very bright. And how do I want to make my movie work? And here's the small Magellanic Cloud in H1 stepping through the cube, so you can see the various different velocities of the H1 as you go through the cube. So all that's working very nicely. We've looked at polarization of a millisecond pulsar and compared it to results in the literature, and we're getting very nice polarization and very nice timing on these millisecond pulsars. And the plot on the right is an OH maser spectrum. There's actually 2 plots there, one made with the ultra-wideband system and one made with a cryopath, and they're basically on top of each other. So that shows that we know what velocity is what, and we've got all that sorted out on the cryopath, and that's also very nice. So the bottom line here is, on the commissioning results, there's that the basic science modes are all working and tested, and we're basically ready to go. So in summary, the cryopath really takes the Parkes telescope to the next level, following the tremendous success of the multibeam receiver that was on the telescope for 20 years. There's many other science applications that I haven't covered here, for example, wide field VLBI. The cryopath will be a national facility instrument, so that's available to the worldwide community based on the merit of your proposal. It keeps paths in the conversations for the SKA long term. At present, we're currently investigating some cryogenic issues that haven't yet been sorted out, but we really hope to commence user-driven science early in 2026. And I'll leave it there. Thank you very much.
Thank you, Simon. Questions for Simon? Yeah, Randall?
Yeah, thanks, Simon. So with the regards to the troublesome RFI at 700 megahertz or whatever it is, I'm guessing that's mobile phones or something.
Yeah.
Is there any plan to try to actively cancel that, or the way it was done in the past? I think Frank Briggs and maybe some ATNF colleagues, did this, and it proved pretty good. Any plans to this?
Well, I mean, as you say, we've been talking about this for 20 years. It's proven kind of more difficult than we originally planned, but it's certainly it's something that we're planning to do for sure, and that we'll need to do, absolutely. Because otherwise, in terms of H1, if you lose part of the spectrum, that's at velocities, that's those redshifts that you're losing. So we'll certainly need to do something. Yeah. But that's a research project in itself.
Questions? Elaine?
Yeah, thanks, Simon. Just to ask about millisecond pulsars in the galactic center. Are there astrophysical reasons why you'd expect such a population? Is it just a question of a high stellar density, or is there something else special there?
It's the high stellar density is one thing, and I think it's also the star formation. In order to get millisecond pulsars are already a border a giga-year old. So we know that there was a lot of star formation back then, so you would expect there to be a lot of millisecond pulsars. And millisecond pulsars need companions in order to turn them into millisecond pulsars, and the large stellar density helps for that also.
Okay, perhaps one more question before we wrap up, if there is one.
The main gamma ray reason why we think this is millisecond pulsar is the gamma ray spectrum looks very pulsar-like.
Finished?
Pulsars are, yeah.
Still time for one more question, I think, if there is one. Can you just say something very briefly, though, about the localization, FRB localization? I mean, the overlapping beams helps. Right?
It's basically the overlapping beams.
Yeah.
So instead of just having if you're at 1.4 gigahertz, you've got a 14-minute beam. Instead of that being your error bar will be a border a few more minutes. But that's still pretty large.
Sure.
Yeah.
Okay. Let's thank Simon again, and all the speakers, actually. Okay, well, Simon says that pulsars are the best thing in the universe, but I quite like the cookies. So let's go have some cookies and coffee. And I actually said something wrong. The second half of this session is after lunch. So see you back here then.